Hello everyone, this is Safa and welcome back. In the previous videos, we studied control systems mainly in the time domain and analyzed responses such as the step response and impulse response. However, time domain analysis is only one way to understand the system. In many practical applications, engineers need to know how a system behaves when the input frequency changes. This type of analysis is called frequency response analysis. One of the most widely used tools for frequency domain analysis is the Bode Plot. In this video, we will learn how to generate and analyze a Bode plot in MATLAB. So let's get started. First, we clear the MATLAB environment. The command CLC clear the command window. The command clear removes previously stored variable, and close all closes any open figure windows. This ensures that we start with a clean workspace. And next, we define the transfer function of our system. Here, the numerator is equal to 100 and the numerator is equal to s squared plus 10s plus 100. Okay, now here we created the transfer function model. The tf command creates the transfer function and stores it in the variable g. Okay, next here we display transfer function in the command window. Okay, this allows us to verify the system model before performing any analysis. Now here, plot the step response of the system. First, we create a new figure window here. Then, the step command generates the step response of the system. The grid command here improves readability. And finally, we add a title and axis labels to the figure. Okay, although today's focus is frequency domain analysis, the step response helps us relate this lesson to the concepts we learned earlier. Okay, now we move the main topic of this video, the Bode Plot. Okay, again here we create a new figure window. The Bode command calculates and displays the frequency response of the system. MATLAB automatically generates both the magnitude response and the phase response. We also enable the grid and add title. Okay. Next, we extract the frequency response data manually. First, here, we define a frequency vector. This command generates 500 frequency points between 10 to the power of -1 and 10 to power of 3 radians per second. Okay, now we calculate the magnitude and phase values. For each frequency point, MATLAB computes the magnitude response and the phase response of the system. Okay, here we use the squeeze command. The Bode function returns multi-dimensional arrays. So the squeeze command removes unnecessary dimensions so the data can be plotted more easily. And here we create another figure window. This figure will contain a separate plot for the magnitude and phase. Okay, here first we plot the magnitude response. The subplot here command divides the figure into two sections. The semilogx command creates a graph with a logarithmic frequency axis. The magnitude values are converted to decibels using 20 times the logarithm base 10. And okay, next we plot the phase response. This graph shows how the phase changes with frequency. The horizontal axis represents a frequency in radians per second, and the vertical axis represents phase in degrees. At this point, our code is complete. Let's run the script and examine the result. Okay. Okay. First, MATLAB here display the transfer function in the command window. We can see that the transfer function here. Okay, this confirms that we are working with a second order system. Okay. Okay, let's look at the first figure. This figure shows the step response of the system. We can see that the response rises quickly, exhibit a small overshoot, and eventually settle at the final value. This indicates that the system is stable. Okay, and let's examine the second figure, which is here, second one. Okay, Bode Plot. Okay, the upper graph represents here we can see magnitude response. The lower graph represents the phase response. At low frequencies, the magnitude remains nearly constant. As the frequency increases, the magnitude gradually decreases. This means the system attenuates high frequency signals. At the same time, the phase decreases and gradually approaches negative on 180. You can see degree. And finally, here, let's look at the third figure. Here, the magnitude here response and phase response. You can see here. Okay, these two graphs contain the same information shown in the Bode plot. Separating them makes it easier to understand the role of each component. The upper graph shows how to gain changes with frequency, and the lower graph shows how the phase shift as the frequency increases. In this video, we learned how to perform frequency response analysis using a Bode plot in MATLAB. We generated the Bode plot, extract the magnitude and phase data, and interpreted the resulting graphs. In the next video, we will continue our study of frequency domain analysis by introducing the Nyquist plots. Thanks for watching.